We now consider more sophisticated control strategies that require smart controllers that use op-amps or a microprocessor. The first and most basic of these strategies is called proportional control. With proportional control, the actuator applies a corrective force that is proportional to the amount of error, as expressed in equation 11.1, where the output of the controller due to proportional control, output P, is equal to the proportional constant of the system called the gain times the error, which is the difference between where the control variable should be and where it is. Consider the position control system shown. A robot arm is powered by a motor. A potentiometer provides position information, which is fed back to a comparator. The feedback signal is called the process variable, shortened to PV. The comparator subtracts PV from the set point, which is shortened to SP, to determine the error E, as expressed in equation 11.2, which is the error is equal to the set point minus the process variable. Referring to equation 11.1, we see that the controller output is proportional to the error. This output directs the motor to move in a direction to reduce the error. As the position of the arm gets closer to the set point, the error diminishes, which causes the motor current to diminish. At some point, the error and the current will get so small that the arm comes to a stop. Assume that a motor-driven arm was originally at 0 degrees and then was directed to move to a new position at 30 degrees. The gain for the system is 2 inch-ounces per degree. Describe how the controller responds to this situation. The solution, the setup is shown. Originally, the arm is at rest at 0 degrees when the set point is first changed to 30 degrees. An error signal of 30 degrees results because the arm is 30 degrees away from where it should be. Error is equal to SP minus PV is equal to 30 minus 0 was 30 degrees. Using equation 11.1, we can calculate the initial restoring torque the system will generate, where output P is equal to Kp times E, or 2 inch-ounces per degree times 30 degrees, or 60 inch-ounces. This means that the motor would initially be directed to create a torque of 60 inch-ounces, causing the arm to rise rapidly. As the arm continues to rise, the controller output to the motor falls, which is shown in figure B. When the arm gets up to 10 degrees, error is equal to SP minus PV, or 30 minus 10, or 20 degrees. The output due to proportion, output P, is equal to KPE, or 2 inch-ounces per degree times 20 degrees, or now 40 inch-ounces. The motor torque has now reduced to 40 inch-ounces, so the arm will slow down. When the arm gets up to 25 degrees, the error is equal to 5 degrees. Output P is equal to 2 inch-ounces per degree times 5 degrees, or 10 inch-ounces. With a motor torque of only 10 inch-ounces, the arm is slowing way down. Finally, when the arm reaches the new set point of 30 degrees, error is equal to 30 minus 30, or 0 degrees. Output KPE is equal to 2 inch-ounces times 0 degrees, or 0 inch-ounces. With the motor torque of 0 inch-ounces, the arm stops. Having the corrective force be proportional to the error makes sense when you consider the following argument. A large error implies there is a long way to go, and so you want some speed to get there, which requires a large torque from the motor. However, when the error is small, the arm should slow down, small torque, so as not to overshoot. Also, note that the system is bidirectional in the sense that the torque will always be applied in whatever direction is needed to reduce the error. For example, consider again the system shown in the previous example. When the arm was directed to go to 30 degrees, the controller output to the motor a signal corresponding to 60 inch-ounces of torque. Later, if the motor were directed to return to 0 degrees, a new negative error would be appearing, causing a new negative motor torque to be generated. The error is equal to SP minus process variable is equal to 0 minus 30 degrees or minus 30 degrees. The output will be equal to 2 inch-ounces per degree times minus 30 degrees or minus 60 inch-ounces. The negative sign of the output would result in a change in polarity of the applied voltage to the motor, which would cause it to run in the opposite direction. Thus, proportional control is capable of driving the arm in either direction. If you had the opportunity to experiment with the proportional control system shown, you would notice that the arm has a springy feel. For example, if you were to push down on the arm, you would feel a restoring force, as if you were pressing on a spring. The more you displaced it, the more it would resist. What you're actually feeling is the control system's correcting force, where the resistance to movement is proportional to the error. The diagram shows how we might model this property for the motor of the previous example. Notice that in the model, the arm is a leaf spring attached to a locked shaft. If we try to push the arm down, the leaf spring resists. The farther the arm is deflected, the greater the resistance force, which is shown in figure B. When the external force is removed, the arm is returned by the spring to the center position. When we command the controller to move the arm to a new position, say 30 degrees, it is like causing the entire spring to rotate, so it is now at rest in a new position and will resist being deflected from that point, which is shown in figure C. Proportional control is simple, makes sense, and is the basis of most control systems. But it has one fundamental problem: a steady state error. In practical systems, proportional control cannot drive the control variable to 0 error, because as the load gets close to the desired position, the correcting force drops to near 0. This small force may not be enough to overcome friction, and the load comes to stop just short of the mark. Friction, always present in mechanical systems, is a non-linear force that opposes the applied force. In fact, the load will not move at all until the friction force has been overcome. Figure A shows another spring model of the proportional control system. This time, the load is sitting on a friction surface in the center of a frame to which it is connected with 2 springs. Figure B shows what happens when the frame quickly moves to the right. At first, the resulting push and pull from the springs drags the load to the right. As the load approaches the new center position, the declining force from the springs is overcome by friction, and the load stops before it gets to the new set point, which is shown in figure C. The steady state error is the distance between where the load stopped and the new set point. This region, on either side of the set point, where the restoring force is incapable of precisely locating the control variable, is called the dead band or dead zone. Other factors besides friction also contribute to the dead band, these being backlash, flexing of mechanical parts, and poor controller design. Let's look at an example of deadband. A position control system has a proportional gain of 2 inch-ounces per degree and works against a constant friction torque of 6 inch-ounces. What is the size of the deadband? The solution: to overcome the friction, the system must cause the motor to output 6 inch-ounces. Because the input to the controller is the error signal, we need to find the value of error that results in a controller output of 6 inch-ounces. Starting with the basic proportional equation, which we saw earlier in 11.1. The output due to proportion is equal to KPE. Rearranging to solve the error is equal to output over Kp, or 6 inches per ounce, divided by 2 inches per ounce per degree, and it equals 3 degrees to one side. With a 3-degree error on each side of the set point, the deadband is 6 degrees. One way to decrease the steady-state error due to friction is to increase the system gain, which is Kp in the equation 11.1, which could be done in the previous model by using stiffer springs. Consider the diagram shown here. It shows the restoring force on the load for two different system gains, Kpa and Kpb. Notice in both cases that the restoring force is proportional to the error. The force necessary to overcome friction is shown as the dashed line. For the lower gain system, the error due to friction is shown as EB. A higher gain system, acting like a stiffer spring, does not have to deflect as far from the set point to produce the force necessary to overcome friction. This system has less steady-state error, as shown by EA. It might seem reasonable to make the gain of every system very high. However, high Kp can lead to instability problems or oscillations. Increasing Kp independently, without limit, is not a sound control strategy. Another source of steady-state error is the gravity problem, which occurs when a constant external force is pushing on the controlled variable. Consider the robot arm lifting a weight as shown. The set point for the arm is 0 degrees, but when the weight is added, the arm sags. Its new position is where the restoring force of the system just balances the weight, in this case 2 feet-pounds. Herein is the paradox of the proportional control concept. For the system to support the weight, there must be an error. The reason: the proportional system only produces a restoring force when there is an error, and the weight requires a constant force to support it. Increasing the system gain can reduce the error, but proportional control alone can never completely eliminate it. Let's look at an example. Specify the system gain, Kp, required to position the robot arm to within 5 degrees of the set point. Total resistance from friction and gravity will be less than 50 inch-ounces. The DC motor has a torque constant of 25 inch-ounces per amp with a 10:1 ratio gearbox built in. A 350-degree feedback pot is connected directly to the arm shaft. The solution: to keep the error down to 5 degrees, the system needs to supply at least 50 inch-ounces of restoring torque when the arm is 5 degrees from the set point. This specifies the stiffness or gain Kp of the system and is shown in graph form. To calculate the required value of Kp, start with equation 11.1. Output P is equal to Kpe, so Kpe is equal to output over the error is equal to 50 inch-ounces divided by 5 degrees is equal to 10 inch-ounces per degree. Thus, the controller must direct the motor to provide 10 inch-ounces of torque for each degree that the arm is away from the set point. However, a controller cannot input degrees or output torque directly. The controller inputs and outputs voltages and currents. The motor by itself provides 25 inch-ounces per amp of torque. But because it's geared down by a factor of 10, the output shaft is 10 times 25 inch-ounces per amp, or 250 inch-ounces per amp, which is the steady-state motor transfer function. Finally, the pot is connected so that 10 volts is equal to 350 degrees. Thus, 10 volts divided by 350 degrees is 0,029 volts per degree, which is the pot transfer function. To arrive at the gain required of the controller, multiply the system gain by the transfer functions, or Kp is equal to 10 inch-ounces per degree times 1 amp per 255 inch-ounces times 1 degree divided by 0,029 volts, and plug all that in and you get 1,38 amps per volt. Thus, the controller must act like a power amplifier that supplies 1,38 amps to the motor for each volt of input. For example, if we want to move the arm to the 30 degree position, we would input a voltage of 30 degrees times 0,029 volts per degree, which is 0.87 volts. Assuming the arm had been at 0 degrees, this command would cause an error signal of 0,87 volts minus 0 volts is equal to 0.87 volts. The 0,87 volt error signal would be converted by the amplifier to 1,2 amps. This initial value of current would drive the motor to produce a torque of 250 inch-ounces per amp times 1,2 amps, or 300 inch-ounces. Eventually, as the error decreased, so would the torque. So when the arm gets to 25 degrees, 5 degrees short of 30, the torque has dropped to 50 inch-ounces, which by design is just enough to overcome friction. One way to deal with the gravity problem is to have the controller add in a constant value to its output that is just sufficient to support the weight. This value is called the bias and is the same value that an open loop system would give to the actuator. The equation for a proportional control system with bias is output P is equal to KPE, as before, plus the bias, and this new formula is called equation 11.3. The bias value is considered to be another input to the controller, as is shown in the block diagram. A 2-pound weight placed a foot from the fulcrum places a constant torque of 2 foot-pounds on the motor. A bias signal, corresponding to 2 foot-pounds, is added to the output of the controller and provides the drive signal to support the weight. This system allows the error to go to 0 because the static load is being supported by the bias signal, not by the proportional part of the controller. However, the bias must be changed if the static load is changed. Note that this bias signal only works at this position of the arm and may make the error worse if the arm is rotated to 180 degrees. An analog controller typically uses op-amps to provide the necessary gain in signal processing. For example, consider the flow control system illustrated. The controller's job is to maintain the flow of liquid through a pipe at 6 gallons per minute. The system consists of an electrically operated flow valve, a flow sensor, and an analog controller. The flow valve is operated with a signal of 0 to 5 volts, where 0 volts corresponds to completely closed and 5 volts is all the way open. The flow sensor provides an output signal of 0 to 5 volts, which corresponds to 0 to 10 gallons per minute. The system is designed so that a sensor voltage swing of 2.5 volts, 50% of its range, will cause the flow value to swing from full off to full on. Therefore, this system has what is called a 50% proportional band. This percent type specification can be translated into a gain factor Kp by rearranging equation 11.1. Output is equal to Kpe, and Kp is equal to output P over E, or 100% divided by 50%, which is equal to 2, which is the proportional gain factor. The analog controller circuit shown consists of 3 op-amps. The first op-amp, U1, is acting as a differential amplifier with a gain of 1, subtracting the sensor feedback signal from the set point to create the error voltage. To maintain a flow rate of 6 gallons per minute, the set point must be 3 volts DC, as calculated below using the flow sensor transfer function. The set point is equal to 6 gallons per minute times 5 volts divided by 10 gallons per minute, which comes out as 3 volts DC. The output of U1, which is the error signal, is fed into op-amp U2, a simple inverting summing type amplifier whose purpose is to provide the proportional gain Kp. To make the required gain of 2, the ratio of Rf over Ri is set to 2, in this case 20 kiloohms divided by 10 kiloohms. Notice that the pot RB can add a bias voltage to the error signal if necessary. The output of U2 must be inverted to make the output positive. This is done with U3, which is a simple inverting amplifier with unity gain.